You know, usually when we talk about a system failure, there's this expectation of a loud, obvious crash.
Oh yeah, like dropping a glass on a tile floor.
Exactly. You drop it, it shatters. Or, I don't know, the software you're using hits a critical bug and you get the blue screen of death.
Right, the cause and the effect are immediate. We really rely on that immediacy to fix things.
But then you step into the world of long horizon AI agents, and suddenly that cause and effect relationship just completely uncouples.
It really does. The diagnostic landscape gets incredibly murky.
Right, like you might observe an AI making what looks like a terrible, illogical decision, but the logic isn't actually the problem at all. The failure happens in silence, long before the system actually crashes.
Yeah, a silent failure.
And that silent failure is exactly what we are hunting down today on the deep dive. So welcome in. We are unpacking a brand new foundational state-of-the-art paper in generative AI.
It's a really fascinating one.
It is. It's called Ask the World Before Acting, Budgeted Environment Probing for World Model Calibration. And this research comes from teams at Emory University, the University of Tokyo, and Location Mind.
Yeah, and it's a remarkable piece of work because it tackles one of the most stubborn bottlenecks in autonomous AI today, which is, making these agents reliable in physical changing environments.
Right. So our mission for this deep dive is to help you understand exactly how long-horizon AI agents think about the world, why their internal reality inevitably breaks down over time, and, well, the delicate, high-stakes balance between double-checking facts and actually getting things done.
It's a tricky balance.
And I promise you, while we're going to get into some complex AI architecture today, the underlying dilemma is something perfectly relatable to your everyday life. So, okay, let's unpack this. The paper introduces this concept of a world model, or a belief table, in long-horizon language agents. And the authors specifically mention systems like React or LATS. I see these terms floating around a lot, but what exactly are they doing differently than like a standard chatbot?
So think of frameworks like React, which stands for reasoning and acting, as giving an AI a continuous loop of agency.
Okay.
A standard chatbot takes your prompt, generates an answer, and stops. That's it. But an embodied agent using React generates a thought, decides on an action, attempts that action in an environment, observes the result, and then loops back.
So it's constantly moving and reacting.
Exactly. And to do that over a long horizon, say 20 or 30 steps, it has to maintain a structured internal memory of what it has done and what the world looks like.
So it's essentially keeping a running diary of the physical reality around it.
Yeah, that running diary is its belief state.
Mm-hmm.
Like if you ask an autonomous agent to make you breakfast, it needs to remember that it already turned on the stove on step 3, right?
Yeah.
Or that the eggs are in the fridge, or that a specific digital tool has been initialized.
Let's ground this. Imagine you're cooking a complex recipe. You firmly believe the salt is on the counter because you explicitly put it there 10 minutes ago.
Right, you have a memory of it.
Right, so you plan your next 3 steps, chop the onions, turn up the heat, grab the salt, assuming it's exactly where you left it. But what if your partner walked through the kitchen and moved the salt?
Then your internal model of the kitchen has quietly drifted from the physical reality of the kitchen.
You are operating in a reality that doesn't exist anymore. So let me ask you this, based on the paper. When the AI eventually fails the task, is the problem that it made a bad decision, or is it that it made a perfectly good decision in a reality that has simply expired?
The data in the paper points entirely to the latter. It's the expired reality. The researchers phrase it beautifully. Actually, they say, drift precedes collapse.
Drift precedes collapse. I like that.
Yeah. The model's belief drifts off screen. It assumes the digital tool is still loaded or the virtual door is still unlocked. And once the agent builds a plan on top of that stale premise, the final action it takes fails. But the failure didn't happen at the action step. It began much earlier in the belief state.
It's like reaching for the salt, grabbing empty air, and ruining the dish. The mistake wasn't the physical reach, it was the outdated assumption that drove the reach.
Exactly. And the paper actually quantifies this lag, which is wild. In their spatial environments, which involve things like navigating virtual rooms and interacting with objects, they found that world state drift precedes action validity collapse by an average of 2.42 steps.
Wait, hold on. So for almost 2.5 turns, the AI is just confidently walking around in a completely hallucinated version of the environment.
Yeah. For 2.42 steps on average, the agent's internal diary is out of sync with actual reality, but it just hasn't hit a wall yet.
That is an eternity in compute cycles.
It really is. It's actively planning based on a stale world. And this completely changes how we evaluate AI failure. Because when an agent fails a benchmark, we tend to blame weak logic, or insufficient reasoning capability.
Right, we say the AI isn't smart enough.
Exactly. But what this research shows is that often the logic was perfectly sound. The world just evolved, and the AI's memory didn't.
Wow. Which brings us to the big question, right?
Yeah.
How do we fix this stale world? And the solution proposed in this paper is called NV probe, short for environment probing.
Yes, and
Basically, it's a direct repair mechanism. Before committing to a task, the agent can spend a step to stop, look at the environment, ask a specific question about its belief, and write the true answer back into its world model.
Yeah, it's the equivalent of you pausing your cooking, looking directly at the counter, and verifying, is the salt actually still there?
Right. Now, if you are listening to this on your commute right now, you might be screaming at the dashboard, just give the AI infinite time to check everything. Compute is getting cheaper. Just tell it to look at the whole room before every single move.
Yeah, it seems obvious, right?
So why can't we just refresh every belief at every step?
Well, the fundamental constraint of both physical and computational reality is that environment interaction is a scarce resource. Every time an API is called, every time a robot's camera scans a room, it costs time, compute, or tokens.
Time is budget.
Exactly. And the paper defines this budget incredibly strictly. They set the probe budget, which they call B, as a strict fraction of the total horizon, H.
Okay, so what's the fraction?
Specifically, B equals H over 4. So, if your agent has a hard limit of 20 steps to complete a task before it times out or fails, it only gets 5 probing actions for the entire episode.
Because checking the salt takes time that you could have spent chopping the onions. You only have so much time before the pan burns.
Right. It creates a brutal mathematical trade-off. If we connect this to the bigger picture, the researchers frame this using something called a Pareto frontier, specifically in Theorem 5.8.
Okay, let's define that for the listener really quick. A Pareto frontier basically means a state of allocation where you can't improve one variable without actively hurting another, right? You are just maxed out on efficiency.
That is the perfect way to look at it. So on one axis of this frontier, you have terminal world model accuracy, which is, how true the agent's beliefs are compared to reality.
Okay.
And on the other axis, you have task success. Did it actually finish making breakfast?
Right.
So an agent that probes too little acts confidently on stale beliefs, so it fails the task because it makes a physical mistake. But an agent that probes too much spends its entire episode verifying the world instead of actually changing it, just runs out of time.
It's like someone who is so paranoid about getting lost that they pull the car over every 30 seconds to check the map. Sure, your mental model of the route is incredibly accurate, but you're never going to arrive at your destination before dark.
Exactly. Every single probe must earn back the task action it displaces. It has to be worth the cost of stopping the car.
Okay, so you have the strict budget, 5 checks at a 20 steps, let's say. How does NV-Probe actually decide which of the dozens of beliefs it should spend its precious budget checking? It needs some kind of scoring system to prioritize.
It does. It uses a 4-part scoring system. NV-Probe assigns a score to every candidate field by calculating criticality, which they call C, staleness, which is, uncertainty, UU, and dependency rule, ST.
Let's break down how it actually calculates those, because if it's just guessing, we are back to square one.
Right, so the model generates these scores mechanically. Criticality, the C score, is found by prompting the large language model to analyze the overarching task and rate how important a specific fact is to the final goal.
That makes sense.
Then staleness, the DADE score, is a literal counter. Just how many steps has it been since this specific fact was last observed?
Right, it's been 5 steps since I looked at the salt, so staleness is high.
Exactly. Then dependency, the DADE score, looks at the immediate next step. Does this belief directly block the very next action I'm about to take?
Okay, got it.
And finally, uncertainty, the U score. This is the model's self-reported lack of confidence.
Okay, I want to stop right there on uncertainty, the U score. Because assuming I'm building an AI, I would look at those 4 metrics and immediately think that uncertainty must be the absolute most vital signal.
You'd think so, yeah.
Like, if the LLM knows it is uncertain about a fact, that's obviously what it should check first, right? Like, I'm not sure if the oven is on, let me spend a token to check the oven.
Well, what's fascinating here is that the data proves the exact opposite. The paper reveals a massive twist. Verbalized uncertainty is actually an anti-signal.
Wait, an anti-signal meaning it actively points you in the wrong direction?
Yes. Large language models are notoriously, aggressively, confidently wrong.
Confidently wrong.
Yes, and the researchers measured this explicitly in their logs. They found a confident wrong rate of 94%, 0.940.
Wait, hold on. 94%.
Yeah.
How is that even mathematically possible? These models are trained on terabytes of human data specifically to predict correct answers. How can an AI be that confident and that wrong at the exact same time?
To understand why, we have to look at how these models generate text. They predict the most likely next token based heavily on their immediate context window.
Okay.
So if the agent's internal diary says, "I put the salt on a counter 5 steps ago," the statistical probability of generating the phrase, "the salt is on the counter," is incredibly high. The AI isn't feeling out the physical world. It's simply reading its own corrupted memory and agreeing with it.
So it's like a corrupted cache in a web browser.
Exactly.
Like when a website updates its design, your browser doesn't feel uncertain about what the site looks like. It just instantly and confidently loads the old broken version of the web page because it's looking at its own local memory, not the live internet.
That is a brilliant analogy.
Yeah.
Yeah, the AI is completely blind to its own blindness.
Blah.
The paper summarizes this in Proposition 5.5. It proves that when wrong beliefs are confidently held, an uncertainty-only policy excludes exactly the fields it most needs to repair.
Because if the system's rule is check the things you are unsure about, the AI scans its cache and says, well, I'm 100% sure the salt is on the counter, so I definitely won't check that.
Right.
But that's exactly the thing the partner moved. So it spends its precious budget checking trivial things it happens to feel statistically fuzzy about while completely ignoring the critical, load-bearing facts that have drifted entirely away from reality.
Precisely. And the researchers proved just how damaging this is with an ablation study.
An ablation study being where you systematically remove pieces of a system to see what causes it to break or improve.
Exactly. They took the ENVI probe scoring system and removed the uncertainty score, the U, entirely from the equation.
They just deleted it.
Yep. And by telling the AI to completely ignore its own feelings of uncertainty, terminal world state accuracy actually improved to 0.488.
Wait, so its grip on reality got stronger just by ignoring its own confidence?
Yes. But here is the catch. While accuracy went up, task success dropped down to a miserable 8.2%.
Whoa, whoa, whoa. Why would task success tank to 8% if the AI has a better grip on reality?
Because, without the uncertainty signal tempering the algorithm, the system swung to an extreme. It forced the AI into a paranoid loop of checking dependencies.
Oh, no.
Yeah, it achieved that high accuracy by spending all its budget verifying the world, leaving barely any horizon left to actually execute the task. It became your paranoid driver, pulling over every 30 seconds to check the map. It just ran out of time.
It sacrificed the mission for perfect knowledge. That is such a delicate, dangerous balance. Okay, so ignoring uncertainty works to fix the paranoid driver problem, but surely the rules change if the route itself is moving.
They absolutely do.
Because the paper tested this agent in 3 specific environments, right? ToolDAG world, GraphNav world, and object state world. Does this mathematical tension apply everywhere?
How the agent behaves and how valuable those probes are changes drastically depending on the nature of the environment. Let's look at procedural tasks first, which is what ToolDAG world represents.
Procedural meaning like step-by-step logic chains, like initialize API, query database, format output. You have to do step A before step B.
Right. These are highly controlled, long-chain tasks, entirely dependent on the agent's own previous actions. And in these procedural environments, the structural score works best.
Which means?
That means relying on criticality and dependency, the C-neat scores. And vprobe actually improved end-state accuracy on ToolDAG world by a massive 11.76 points over just randomly or periodically checking.
Well, sure, because it's smartly checking the exact prerequisites for its next move. It says,
Wow.
before I format the output, let me verify the database actually sent the data.
Exactly. But the strict probe action trade-off remains, because
Okay.
even if you are checking the right things, every check competes with that long, demanding chain of required actions.
Right. Okay, here's where it gets really interesting. What happens when we move out of the highly controlled procedural world and into the messy spatial world?
The spatial tasks.
Yeah, environments like GraphNav world or object state world, where the AI is navigating physical style rooms and finding items.
Spatial tasks are fundamentally different. There are often short-chain tasks, but more importantly, they were subject to exogenous changes.
Exogenous meaning changes caused from the outside.
Right. In procedural task, the state changes mostly because the AI took an action. But in a spatial task, someone else might lock a door.
Ah.
Another agent might move a key. The wind might blow something over. These changes happen completely outside the AI's action history.
So the AI has literally no context clues in its own log to suggest anything has changed.
Exactly. And because the AI has no record of the change, its self-reported staleness is just as useless as its self-reported uncertainty.
Oh, wow.
It has no reason to feel uncertain and no reason to think the belief is stale if a door was unlocked 5 minutes ago and the AI hasn't touched it since.
So the S and U scores, staleness and uncertainty, are completely dead weight in the physical world.
Dead weight, which means we have to rely entirely on the structural score, the C plus D, criticality plus dependency, and when the researchers applied only the structural score to spatial tasks, something incredible happened. The budget trade-off, that Pareto frontier we talked about, actually vanished.
Wait, the absolute mathematical limit just goes away.
It vanishes. Using just the structural score, Pareto dominates everything else in spatial tasks. It achieves higher world state accuracy and higher task success simultaneously.
That's amazing.
Yeah, because spatial action chains are shorter, the cost of probing is very small relative to the massive benefit of correcting a belief about a blocked path or a missing object.
So what does this all mean? Let's bring this home for you listening right now. If you are designing or even just interacting with autonomous AI agents in the real world, the takeaway is pretty stark.
It really is.
You cannot just trust an AI's self-reported confidence. When a large language model says it is 100% sure the door is unlocked, it means almost nothing if the physical world has been moving around it.
You have to treat environment checks as budgeted actions. They cost money, compute, and time.
And to spend that budget wisely, you have to use type-aware structural cues. You don't ask the AI what it's confused about. You ask, what fact is most critical for the very next step? And you force it to check that. You keep its world model tied to reality without paralyzing its ability to act.
And this raises an important question, actually, one that really builds on the implications of this paper.
What's that?
Well, we spend so much time in the tech world worrying about whether AI models are smart enough to plan for the future. We obsess over raw reasoning power, parameter counts, and logic puzzles.
Oh, totally. The endless push for artificial general intelligence.
Right. But if an AI's internal reality inherently drifts and verifying that reality costs precious computational actions, perhaps the real bottleneck to AGI isn't raw reasoning power at all. Perhaps the ultimate bottleneck is the sheer, unavoidable friction of physical reality.
Oh, that is fascinating. You're saying the limit isn't brain power, it's the cost of syncing up with the chaotic real world?
It's the cost of constantly calibrating a synthetic, text-based mind against a universe that doesn't hold still. If an AI has to spend a quarter of its operational lifespan just making sure the metaphorical salt hasn't moved on the counter, how fast can it really operate? How autonomous can it truly be in a dynamic environment?
That is a phenomenal point to end on. I mean, you can have the most brilliant chef in the entire world, but if they have to spend 25% of their time opening the fridge just to make sure the ingredients haven't randomly teleported, they're not going to get many meals out of the kitchen.
Exactly.
Reality is a very expensive thing to keep track of. A huge thank you to you, our listener, for joining us on this deep dive. Whether you are building the next generation of AI agents or just trying to understand why your smart home assistant seems to lose its mind every now and then, we hope this gave you a new lens to view the problem. Next time you're absolutely confident you know where you left your keys, just remember, you might be 94% confidently wrong.
Until next time.
Keep questioning your world model. Catch you on the next deep dive.